Thank you. Good morning, everyone. Seems coffee wasn't strong enough. Good morning. Before I start, I want to say thank you to the organizers of the conference and also the leadership at ISARC for inviting me and being here. I really appreciate the opportunity of sharing with you a journey. So what I want to do today is to tell you a story of how I started working at the interface of computer vision and construction, and how that is story of research project transformed into a visual production management system that is currently being used on thousands of projects around the world. Let me see if I can get this going here. I have a lot of visuals and I'll be happy to share them with you. So by now, you probably heard two terms from me, computer vision and construction. That's what I do. For the past 15 years of my life, I've been exploring ways by which we can take advantage of images and videos. Why? Because I believe in visual data as a medium that we can use to communicate how much work gets done to owners, to contractors, subcontractors. That's our common language. If you show an image to anyone, they would understand it. And I've been trying to find ways by which we can use images and videos to close the feedback loop in project controls. Every project starts with a plan, whether that's a design or construction plan. And what I've been striving to do is to see how we can take advantage of visual data to capture what really happens on the job site. So at any point in time, you can see what is there versus what should be there. And I've explored quite a few different applications. The one that I'm going to focus on today is a project that you see on the top left corner, automated progress monitoring. But before I get into that technology piece and speak about the specific solutions that I have, I thought maybe it's not a bad idea to look into the status of the industry today. I know we have audience from all around the world, but I thought, I'm just coming from the US, so I should be sharing with you things that you're probably hearing on CNN, BBC every day, that there's a potential for a recession happening in the US. And I question that. In fact, this past week, Dodge Momentum Index was published, and the numbers that are coming out are pretty exciting. Construction value in the United States has reached $1.8 trillion. This is the highest amount of money that we've ever invested in construction in the United States. And in fact, that DMI, as you see I have up on this slide, was up for 0.3%. What it means in layman terms, it means more construction projects are coming up in 2022. And then we say, so what happened? You had pandemic, there were impacts of changes, and there's all kinds of conversations about inflation or stagflation. So how is it possible that there's more work to be done? There's been a shift. The new projects that are happening in the US is because a lot of manufacturing industrial projects are coming back home. At the same time, we just passed a new infrastructure bill. That means more money is being invested. But if you look into this number, you would see still a large percentage of that, roughly around 40% of that goes into our labor. And when it comes to how we are communicating and coordinating work that the labor will be able to do, and I'm using the word labor very broadly, encompassing engineering and management too, you see a lot of waste. So if you do the math of that 35% to 40% times the $1.8 trillion, that number is roughly around $250 billion. That's what I would call productivity opportunity. For those of you who are into numbers in construction projects, I want to give you an example. The most recent exciting project that I've come across myself is SoFi Football Stadium in California. It was the one that was hosting the American football game. And that project finished for $5 billion. So you're looking at roughly 50 of those stadiums that we can add every single year if we just focus on solving our coordination communication problem. But you may say, so what does that mean for those of us who are engaged in construction projects? That means when you have these coordination and communication problems, most likely your projects are finishing behind the schedule or over budget. These are the numbers that Dodge have published over the past few years, that especially when it comes to mega projects where coordination matters, that number is almost 80%. So 80% of our projects still today, with everything that we've done with research, every technology we use happens to be behind the schedule. Now, we have actually done a survey. The survey was initially done by Dodge Data and Analytics, but I had an opportunity of doing this 2 years ago at ENR Future Tech, where we asked an audience of owners, contractors, if you're about to pick one metric that really matters to you during the construction phase, what would be that metric? And of course, I'm sure everyone in the audience will agree with me that the answer to that should be design. The more time we spend on planning, the more time we spend in design, we can actually save a lot. In fact, there's data out there that shows if you spend $1 extra in design, you can potentially save up to $7 of your construction work. But we wanted to focus on the construction phase. So the owner has already bought into the idea of design. Safety. Why you would say, why safety is not the most important factor? Because we trust contractors to have a safe environment, quality. We have specifications for that, budget. If there's one thing that the owners are really good at is managing their budget. But if there's one variable that is extremely difficult to manage, that variable is a schedule. And that impacts your bottom line ability to be able to generate revenue from the asset that you're building. So to better understand what are the sources of challenges that we have with the schedule, I want to take you back to basics that we all do. Every project starts with a plan. We go and execute that plan, and we get together in a timely fashion to see if we can learn from our mistakes and successes and use that as a base of updating. Doesn't matter if you're implementing earned value analysis or you're practicing lean construction, and I know in Latin America are actually pretty advanced. In this cycle, there are 4 specific problems that are contributing to this problem of coordination communication. One, as an industry, as a academic background, we've come a long way in improving the way we actually offer scheduling capability to projects. But when it comes to implementation, we still have a lot of challenges. Ideally, we want to have teams engaged in our process. We want to have those last planners involved so we can proactively identify challenges and address them, use the feedback where it matters. But unfortunately, there's a body of empirical observation that demonstrates that when you engage people in those processes, you need to have a champion on the job site to be able to help facilitate that coordination communication. And the moment that you lose those champions, you go back to the old-fashioned retroactive practices that all we do is we get together in a meeting and we react to the mistakes that we've made over the past week. Second issue is that while we have plans in place, we are not good in implementing our own plans. We've been surveying project teams on all kinds of reasons why projects are unable to execute. And there are all kinds of reasons that superintendents report back. Plans changes, we show up at the job site, our work area is not available to us, we underestimated the effort. If you look closely into these root causes for delay, almost 80% of them are preventable. The challenge is project managers and superintendents do not have visibility to these problems in time to make an action to be able to bring the project back on schedule. Third problem is the way we are communicating and measuring performance. We've come a long way. In this conference, yesterday, we heard all kinds of methods that can be used for automated progress tracking. But this picture that I have is actually from a recent visit that I had to an electrical vehicle manufacturing plant in Michigan, one of the most advanced companies on the face of Earth. And this is the practice that they do. Every week, they get into a coordination meeting and they ask the subcontractors to color code how much work was done. So from the time that the problem happens on a $500 million project to the time that you learn that you have a problem in place, you've effectively lost 5 days of work, and that translates into big money. I'm going to give you another example. One of the hottest areas of construction in the United States is data centers. We build a lot of data centers, Facebook, Microsoft, Amazon. These are $500 million projects each. They're done in 10 months. So you're looking at about $5 million of construction work a day, $5 million a day. So if you're losing 5 days of work to understand that you had a problem, you have a big problem to solve. But the problem is also slightly different. Where do you want to have that feedback? Do you really want to understand progress compared against your 2D, or you want to have that against your plan to begin with? The challenge is that these project teams, they have directors of scheduling, but there are other ones who are on the job site. So they're always missing that feedback loop of using that data to truly update the base of the plan. So the plans are being updated based on what, politically correct, we call it engineering judgment, but rather our gut feeling of how much work can be done. So there are 4 problems: coming up with a plan, being able to execute that plan, monitoring how much work gets done, and using that data as a feedback to keep iterating and updating the work. So I had an interest to figure out how I can solve these problems. I used to work for a large construction company at the time, and we had 1,500 projects a year. And at that time, I was looking to how much money we were investing in all issues that are associated with daily reporting. And I, started using that as an academic approach. So I tapped into the data exists. And I'm going back 15 years ago. This was at the time that the BIM was making its way into the industry from an MEP coordination. I was actually practicing it in British Columbia in Canada at the time. So I came into this world thinking that BIM is going to make a huge impact. And I thought, what if we integrate them with the schedule, specifically production level schedule? So you all agree we can actually create a form that can be used for constructability reviews and as a basis of tracking progress. Then I thought there's another opportunity. Why don't we tap into visual data? There are different types of visual data that are being captured on the job site. And I thought, it's great. There's a growth in it. These visual data are simple to be used, and maybe we can actually use them as a base of feedback. The most common type of visual data capture, we walk on job sites, we take pictures with our cell phone. Over the past 20 years, we've had professional photography making its way into construction because owners love to make sure they have, for liability reasons, they have a full documentation. Time-lapse cameras, 360 cameras, drones. Today, construction market is the #1 market for drones. And laser scanning, as you've heard, and we have experts in the room, including our Professor Fred sitting here, that obviously you can use them for all kinds of quality control purposes. So why don't we tap into this visual data that already exists and find ways that we can use it as a feedback against that plan that would be BIM plus a schedule. So I came up with an idea long time ago that what if you come up with a way that we can automatically superimpose that 4D BIM model on a picture? And why don't we find ways by which maybe we can compare that photo against the 4D BIM and automatically color code areas behind the schedule in red, areas that are on the schedule in green. So that begs a question of how does it solve my problem? So let's look into that feedback loop that I was showing you before. So that project controls loop, you can now call it computer vision project controls or a project control cycle that is driven by visual data. So in this case, that 4D BIM that I showed you before can be helping us with creating a reliable plan that can address problems that we have in early phases. Our visual data can formulate what I would call reality models that can be aligned over time. So 4-dimensional reality models that can be twinned against the BIM. So I'm using the digital twin terminology to twinning reality against the design. So we can actually address coordination and communication problems. And if we can find ways by which we can automatically compare the two through analytics, maybe we can actually come up with proactive risk management practices. So now go back into the technical problem that we have in hand. So if I want to solve this, I have 3 important questions that I have to answer. How would I be able to automatically align a 2D image against a 4-dimensional model? How would I be able to detect and characterize changes that are happening on the job site to reflect how much work was done? And lastly, how would I be able to relate these changes back into that plan? Now you may say, easy, why don't you try to find a number of points in the picture, and why don't you find a number of points in the model and see if you can align them? Well, we all know design is an abstraction of the reality. So there's always a challenge of maturity in mapping against the design. Second, we don't know where these images are taken from, and we don't want to dictate that either. So we need to find ways by which we can automatically match. Now, I'm going to take you back to some of the basics of computer vision. In computer vision terms, it means having a pinhole camera model that, for sake of simplicity, with 11 degrees of freedom, that you need to understand how the camera gets positioned and orientation against a 3-dimensional scene and a number of intrinsic parameters associated to that. So I came up with an idea. What if, instead of me trying to match every picture against the model, I find a way that I can marry these pictures and stitch them together to generate a reality picture of what's happening on the job site? If I can do that, then maybe I will be able to marry that against the BIM. So fast forward, that technology has actually made it into the market. We happen to have a solution, and the one I'm showing is an example of that. That basically takes a collection of photographs you have on the job site that can be taken with a drone, can be taken with a 360 camera or your cell phone, and automatically generates a reality model of the job site at any point in time. Now, this happens to be a $150 million project in the city of St. Louis, a high-rise structure, as you can see, and there's a core concrete going up here, an excavation site right here. What the superintendent project manager would be able to do is you click on a location, the system would automatically take you to that most relevant image, and guess what? Now your images are measurable. You can go ahead and measure any dimension that you desire here. So if I can solve that problem, I still need to figure out a way that I can bring it into alignment against the BIM. Now, there are all kinds of automated techniques that can be used to solve this problem. I chose to manually solve this. And what it means is we identify a number of control points that we have between the BIM model and the reality. And maybe I can solve this as a similarity transformation problem. Now I can go ahead and have BIM automatically align reality data. So if I can achieve that, then I can go back into my computer graphics techniques and find ways by which I can render the BIM model on top of the picture. So at any point in time, you can see a color-coded picture that, for example, shows you what are the contractors you have on the job site, how much work is being planned, and use that as a base of coordination. So if I can formulate that 4D BIM, I can formulate that model, then I can go back and see if it can automatically detect progress. So here you see an example of a schedule. It's been integrated against the model. and you can actually see the color coding. So obviously I had to think about how I can automatically solve this. In our early days, the approach that we took was pretty naive. I don't intend to get into any formula today, but the idea was very simple. We're going to look into visibility that we get to elements from pictures, and we look into the visibility that we have to BIM models from the same camera positions. And if we can map this into a machine learning problem, maybe we can automatically color code components. And we actually did this a long time ago. And the numbers that we had, I mean, for academic exercise, good, not bad, 80, 85% range, and you see precision recall graph. But let me show you examples of failure when you start putting this into practice. So not bragging about good numbers. When you look into physical deviation assessment, you would run into these types of problems. A false positive example. This algorithm at the time was automatically detecting if elements are in place or not. You're looking at a concrete foundation wall. The concrete foundation wall is not finished in this area, but the algorithm made a mistake and automatically detected as correct component. Or here's another example where it was unable to reason that the element is not fully visible. So it assumed that the element is not on the job site. So it begs the question, can you go back to the basics of computer vision and explore what else can be done from these images and naturally gravitate to appearance data? I've already explored geometry, and maybe appearance is the other component I can tap into. But there are two requirements. If I want to understand appearance, this is the problem that I have to solve. You're looking at the same foundation wall. You need to be able to identify formwork. You need to be able to see if the reinforcement bar is in place, placement of the concrete itself, finishing surfaces. If it was a facing wall, then you would have had waterproofing, membrane, insulation, and maybe cladding. And of course, in this case, you have backfilling. There are two problems that are unsolved from an academic perspective. One, we do not have formal representation of construction sequences. Now, I'm very happy that I have this opportunity to present this at University of Los Andes. I was inspired by the work of Diego Echeverri, who unfortunately passed away about 10 years ago. He graduated from University of Illinois many years ago, and he came here. He published a paper on how we can actually create work templates that can be used for learning formal representation of the schedules. So I thought, what if we tap into that, not for the purpose of planning, for the purpose of learning, what is it that we have to be detecting? And then we also obviously have the issue of dealing with level of development per discipline in a building model, and then what we have to do with the granularity of the schedules. So again, fast forward, what has been beautiful is in our domain, we've had the opportunity of working on quite a few different algorithms that can automatically detect construction materials from pictures. There are data sets that are publicly released. Yanis Brilakis has published some of this work. We've contributed to some of that, and we've brought it into the practice of progress monitoring. Obviously, when you marry geometry and appearance, you can have a better performance. So there's no doubt there, and we've been able to prove that. Once we look into these formal representation of activities, we thought, what if we tap into the BIM? We also model these relationships in BIM. Can we tap into those relationships, the ones that Diego Echeverri here formulated a long time ago, and use that as a base of recognizing components when we have limited visibility? We actually did this work some time ago that shows another 6% improvement that can be made on the purpose of progress monitoring. So now we had all the elements of research that have actually solved the problem, but all we have is a research prototype. We had to start thinking about how do we engineer this solution? How do we bring it into a level that can actually scale to some of the challenges that we have with construction data? So I want to start by showing you an example. We started bringing in into a mode of testing this algorithm, and we tested it on a significant large number of construction projects with every part of it we could find, from Miami to Japan to projects in Sacramento, California. And we learned a lot from that exercise. Not only we learned how we have to optimize the algorithm, but we learned that there's a need for a web-based system that will be able to display this data. And if you're dealing with web-based system, you have a totally different memory limitation. So now you have to optimize algorithms that can be used for representing even point cloud data. Again, I'm not going to get into a whole lot of details. That pipeline of algorithms that gets used in computer vision needed to be optimized so that you can actually run this on some cloud offering, let's say Amazon or Microsoft. So you'll be able to help contractors run this algorithm every single day as much as they desire. So worked on a number of algorithms that contribute to that. But when you bring these computer vision into the practice, you learn a lot from it. we learned that if you follow standard structure for motion practices, you're likely going to fall into three problems. One, there's no guarantee you can completely capture the entirety of the scene. Second, you heard a lot on drift problem with the SLAM and structure for motion algorithms. In fact, we had a presentation from the University of Cambridge yesterday focused on the same problem. There's no guarantee that our optimization would be able to converge into the global optima. We may be stuck in local optima. So you also have this problem. And of course, when you're dealing with image-based point clouds, they're up to scale. They're not in any specific side coordinate system. So we came up with a new idea in computer vision, which is actually inspired by what we do in civil engineering. What if we assume that we have some understanding of the geometry in the scene and use that information to optimize a structure from motion, which we call it model-assisted structure from motion. And the idea was very simple. It's actually inspired by our surveying practices. If we start capturing a site by knowing that we have a number of control points, what we can do is we can solve for what we call a perspective endpoint algorithm that formulates an anchor camera, one or a few cameras that have been optimized to show you exact location of the beam model. Then when it comes to the optimization, we can actually run into what we call a model constraint optimization that in basic terms, this is what it means. We optimize it for one picture. We bring that through homography transformation into other images. And then once we have a collection of these images, we run it through that model constraint structure for motion. And maybe using that information would actually solve these three problems that I mentioned you before. We wanted to actually publish this in computer vision and computer graphics community. So it was important for us not only benchmark it against construction data set, but also benchmark against data that is commonly used in that community. So you can actually see we actually compared this against the Middlebury data set. And at the time that we published this work, the more CGraph facing benchmark for performance was actually a system released by Microsoft called Microsoft PhotoSynth. So you can see when you tap into the idea of leveraging surveying data, you can actually minimize a lot of this drift and rotation problems that we have. But in simple terms, this is what it means. When you do a capture for site like this, your structure for motion may give you wrong angles, but if you're actually optimizing for these surveying control points, you might be able to actually address the accuracy issue. And because you're actually using a model constraint approach, you will actually end up getting more complete reconstructions because their likelihood of registering images goes up dramatically. So it gives you better completeness. Second issue was that why are we only trying to perform material recognition as a texture recognition problem, standard computer vision problem? Well, we have an understanding of geometry in civil engineering. We know what micro texture we're expecting for every type of material, and we also know what macro texture we're expecting. We know elements that are supposed to be vertical, elements that are supposed to be horizontal. So we actually came up with a geometry-informed material recognition. This is a work that we published in CVPR conference recently. That again brings a very simple concept from civil engineering. Instead of merely looking to it from a texture recognition problem, use geometry and tapping into a deep learning architecture that we have in here that can actually demonstrate that the likelihood of recognizing material broadly goes up. Now, proactive change detection. We actually started representing these color-coded components to project teams, the green and red, right? That shows you the past. But here's the problem. After a few efforts, they would get back to say, well, you're only showing us the past. Can you tell us a little bit about the future, maybe the near-term future? What is likely going to go wrong for us in the next 2-3 weeks in our look ahead schedule? So we actually thought, what if we tap into trend analysis in very simple terms? A hybrid machine learning approach that you would marry regression analysis because it's easy to understand with networks because they're easy to train. So you can actually come up with a strategy to forecast the likelihood of delays in the future and color code components and work locations that are at risk for delay and bring that into the coordination meeting to see how people would react. This is a project in Chicago. You see a superintendent is running the meeting by highlighting 5 locations that are marked at risk for potential delay, a delay that hasn't happened. Look into the dynamic of this meeting. The superintendent for concrete placement is actually standing up, and now he's engaging in the conversation because he has an incentive to be part of this. That location is where his crew is going to be placing concrete. That location is likely going to be delayed. So if he solves that problem for the project, it's going to maximize his own productivity and the profit that he takes from the project. So now we've gone from that retroactive practice to a more proactive practice. We actually deployed this on 2 job sites. One of them took us 2 years to actually look into the behavior changes that we see in these coordination meetings and measure that. We measure that using percent plan complete, or we didn't do much. When the superintendent takes an action on a project like this, based on risk or delay, obviously PPC can go up dramatically. So we took it from 46% to 70%. And the number of tasks that are being delayed based on lean practices go dramatically down. So there are a couple of takeaways before I get into some of the challenges that I faced. One, when we work on these computer vision algorithms, there's a part of it that is truly an academic work, but we also have to worry about engineering them because we are solving an industry problem. And these engineering problems are things that matter. And these are not things that the startups or technology companies are capable of doing. I believe that this is on us. Communities like ISARC are the best communities to actually present and work on these problems that interface prototypes to things that will truly scale in construction. Second one, there's a ton of opportunity to bring civil engineering concepts back into AI work, especially based on geometry. Merely looking into appearance is not solving our problem. Tapping into that geometry can help us with recognition, can help us with 3D reconstruction. And of course, when you capture data at a scale that matters, you can get into a better type of inference algorithms. Now, what I showed you was commercialized 7 years ago. We raised a significant amount of money for this. This is a solution that's commercially available and used on thousands of projects, from large electrical vehicle plants that they demonstrated before to small McDonald's and Dunkin' Donuts. Basically marries 3 different types of data: your reality capture data, your models with 72 different file formats and schedule, and it ties that into your financial system so you can use it for payment verification. Now, when I was going through this journey, I had a few lessons learned that I thought I should be sharing with you. I'm calling it crossing the chasm for the following reason. In academia, in most of our work, we interface with the top industry people. These are the people that are more open to the usage of technology. They're the ones who are first adopters. But when you start looking to the masses of construction, you realize that convincing people to leverage technology is a whole different problem. And there are a few opportunities that we can tap into. Low-hanging fruit opportunities for making an impact, data, and does it truly fit my workflow as opposed to changing that, and the way we measure value. So let me start by showing that. So in early days, I was not really worried about how we're going to be doing this capture, but when we started scaling it, we truly recognized that we have a problem in place. So we actually came up with an algorithm that can tap into 360 video cameras that can be mounted on a hard hat. Why? Because we wanted to make sure we can offer you an experience that people can use. Point cloud data is actually a great source of data, but unfortunately, through our user experience analysis that we performed, we learned that superintendents do not understand point clouds. They like images, and they like measurable images. So we had to come up with an algorithm that can transform our point clouds into this rather Google Street View experience that is measurable with these blue donuts that you can walk around. And it automatically generates a floor plan for you from your video capture, so you can see where you are against the scene. And now, instead of measuring off of a point cloud, you pick pixels, and you'll be able to measure the surfaces against that. What is the value? The first most tangible value that you can imagine that helps sales process. It minimizes how much time you have to spend to travel to your job sites, and that already sells for the solution by itself. Second problem, when you start implementing these algorithms at large, you would notice that indoor environments actually create all kinds of challenges. When you have flat surfaces, a lot of these reconstruction algorithms would fail. So we actually tapped into a number of deep learning steps so we can actually densify the point cloud as a function of the shapes that we can recognize. This is state-of-the-art in structure for motion, and this is what we were able to achieve in one of our earlier prototypes. Unfortunately, the challenge that we have is the following. When you're dealing with the startup companies and technology companies, they tap into open source projects and they tap into blogs that exist. They do not read our papers. It's very unfortunate. We do not always have the opportunity. So I think it's actually a huge opportunity that we're losing by not having more of our industry people, especially technology companies, to be sitting at an event like this, listening to see what we do and find ways that we can collaborate with them, because we can actually solve their problems. Another problem. We came up with an interface that manually aligns 2D drawings against reality captures. Then we realized that people have to do this automatically. So we came up with an algorithm that would automatically align your captures against 2D drawings automatically. Does it always work? No, it fails. Then as a backup, you have a manual interface. You go back and make your alignments. Here's an example of that. This is a McDonald's store. So I thought I should show you also a very simple example. You see the store layout on the left corner, and it's being automatically aligned against the point cloud. Measuring ROI. When we started selling this, it was a whole different game for us in terms of what is it that we have to do. Here's where I stand today. When we measure impact and value, we need to measure it at two levels, at the project level and also at the persona level. Because oftentimes when we are selling it to the project teams, it matters to them. What is it in it for me? So as you can see here, we've looked into the savings on quality control at the personal level. What is it for superintendent that you no longer have to chase down the subcontractors and find a way that every party that's engaged in the project will be able to benefit from this technology. Here's another opportunity. When you start interfacing with the startups and technology companies, you can actually leverage a product to solve an industry problem. And through that product, you can actually capture the data that actually truly matters. This is another learning that we had. When we start looking to progress monitoring and automation, many of the techniques that we've invented over the years do not scale for a simple reason. BIM models are not mature. Schedules are not good to begin with. So we've actually come up with a number of algorithms to automatically recognize progress independent of BIM models, independent of the schedule data, and reflect that against a 2D drawing. So you can actually see changes over time. Here's another point that I thought maybe I should be challenging our own community. We think about AI systems as two parts, algorithms and data. And as a community, we spend most of our time on coming up with methods. But there's an emerging body of observation that shows that spending time on data preparation is likely going to have a higher impact on coming up with models. And this is not just me saying that. I have this from Andrew NG that you can actually see on model-centric conversation on AI. This is a very simple case of steel defect detection. Increasing the data would actually be able to improve the performance by about 16%, but changing your machine learning algorithm, changing your recognition algorithm, changing your deep learning architecture is likely not going to make that major impact. So what I'm thinking here, the opportunities are the following. Figure out ways by which we can deploy our technology on the job site and use that as a way of capturing more data. When we get the data, share that data that as a community, we can actually benchmark our algorithms against this. Once we have better data, we would solve that industry problem first, and then we'll be able to come up with more creative ideas of continuous refinement of these models. Another big opportunity, everything we do in our industry is based on design and schedule. Why don't we come up with PBR algorithms, physically based rendering methods that can actually generate synthetic data that can be used for augmenting many of these recognition problems that we have. And it's on us. We are the ones who have that opportunity. So I'm showing you an example of recognition on BIM models that can generate millions of photos that are all labeled automatically. Or schedule data. We have a ton of knowledge data that's been embedded into that, and we've tapped into that to close the feedback loop. So all I've tried to show you is to show you a number of problems. And you may say, so where are we going from here? We have this three-part problem. We have the construction technology problems. We have what we are interested in focusing on as academic research, and a startup community that acts between the two. And there's a ton of money that's being invested in technology companies today. It's actually more than $4 billion right now. And when you look into that number, you would see that there's a lot of investment. If we can actually solve a way that we can bring startups, technology companies, and academia on the same place, perhaps we can start addressing these problems. And I think this can actually be done if we build a community. And I believe ISARC is probably the best opportunity to streamline this process. Let's invite more startups, let's invite more technology companies, and let's find ways that we can solve their problems, because their problems are the ones that truly deserve our attention. That's all I have to offer you. Thank you very much for your attention today.